All right, let's work an example of 3D equilibrium of a particle. We're being asked to determine the tension forces in all the cables. There are 1, 2, 3 cables here that are supporting this hanging cable right here that's got a weight at the end of it. The weight is 3 kips acting downward in the negative y due to gravity. The red cable here, AC, is defined not by locations of point C, but rather by these direction angles that we've learned about, with a theta x of 115 degrees, a theta y of 74.5 degrees, and a theta z of 150 degrees. Point D here has coordinates of 5 feet in the x, 4 feet in the y, and 3 feet in the z. And cable AB here is running directly along the positive z-axis. So the green weight here and the orange cable AB are both very easy to define in 3D. The other two are a little bit harder. So we're going to determine the tension forces in all cables. First step, draw the free body diagram. So I've started it. Here's my particle at A, and now instead of having my supports at the other ends, I've cut through each of the cables. So now I've got vector heads on them pointing away from point A. All of them are emanating out from point A, so they're all shown as tension. I've labeled them because I don't know their values besides W here, which I'll put on there in a second. But right now I've got all their labels. And let's calculate these easy vectors first. We got W of 3 kips. And since we're doing a 3D problem, let's put everything in Cartesian vector form like I mentioned here. So not only is it 3 kips, but it's actually negative 3j kips because it's acting in the negative y. FAB here is going to be equal to the magnitude of FAB, which we don't know what it is. That's one of the things we're solving for. So FAB here is going to be an unknown, but we do know that it's acting purely in the positive k direction. So that vector would be written as FAB times k. And then for FAC, this red vector, we need to use those direction angles. So we know that FAC is going to be equal to the magnitude of FAC times, I've gone ahead and distributed FAC through here, right? This is really the magnitude of FAC times this unit vector here. All right, so theta x was 115, theta y was 74.5, and theta z was 150. Those were all given in the problem statement, which gives us these values. Cosine of 115 is minus 0.4226. In the I, 74.5, the cosine of that is 0.2672, and the cosine of 150 is minus 0.8660. So in Cartesian vector form, keep in mind that those are all from the positive axis. Doing it the scalar 2D way and the 3D Cartesian vector way has a little bit of differences. FAC, we know, is acting actually to the back and up. And in the scalar method, you kind of learn to go ahead and assign manually those positive and negative signs appropriately. Note here that really these vectors, they're always going to be plus, 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 and let the cosines tell you what's negative. So 115 degrees is going to give you that minus, and 150 is going to give you that minus, where 74.5 gave you a plus. So these minus signs come directly from the cosine calculations themselves. And I'll put that up here on my free body. So now I've got 1, 2, 3 out of the 4. I just need FAD left. So to calculate FAD, let's use the position vector concept. We know that point D was at 5 feet, 4 feet, 3 feet, and the A is at the origin, so 0, 0, 0. So I end up with 5i plus 4j plus 3k feet is the position vector to get you from A out to point D, which is no longer on this free body because I kept the part that I was keeping and I was getting rid of the part I was getting rid of. The magnitude of that is the square root of the sum of the squares of 5, 4, and 3, so that gives me 7.071 feet. So now I'm going to divide the Cartesian vector form of AD by the magnitude of AD, which gives me the unit vector AD, lambda AD, is going to be equal to 0.7071 plus 0.5657 plus 0.4243. Again, no units because the feet's cancel. All right. Now to get FAD into Cartesian vector form, I just multiply the magnitude of FAD times the unit vector. Well, the magnitude of FAD is the unknown, what I'm looking for. So I'm going to distribute that through, and I'm going to get this vector right here. And I put that up there. All right, so now we've got all of our free body diagram pretty well defined. I don't have any angles on this free body. In 3D, sometimes you will, sometimes you won't have the angles. Here, I mean, I could have written the coordinate direction angles for FAC, but I went ahead and used them and calculated this, and this actually gives you all that information. It might not be right in your face, but it is all there. So this does meet the muster of having everything on the free body that I need, because now I can just look at this free body and build my scalar equations of equilibrium. And to do that, I do sum of forces in the x equal to 0. And what are the x values? All of the I values. So there's not going to be an I value in this one, no I value in this one, but these two have it. So there's my equation. 0.7071 FAD minus 0.4226 FAC. So I take that I value and this I value, add them up, set their sum equal to 0. I'm going to call that equation 1 because I'm going to do a simultaneous solution of equations here to solve this. So I'm going to go ahead and just name it equation 1 for this example. Sum of forces in the y, you guessed it, going to do the same thing with my j terms. So now I'm going to have 3 values. I'm going to have 0.5657, 0.2672, and minus 3. So I have 0.5657 FAD plus 0.2627 FAC minus 3 kips equal to 0. I'm going to call that equation 2. Now I'm going to sum forces in the z. And I'm going to have everything but the weight itself is going to be acting in this one. So 0.4243 FAD minus 0.866 FAC. And then FAB in its entirety is working in the z-axis. Sum all those equal to 0. I'm going to call that equation 3. Okay, those are my same 3 equations. Now let's solve this system. You can solve a system of 3 unknowns with 3 equations. You should have been doing this for a long time, since way back at the beginning of high school. But I'll go ahead and solve it here one way. There might be faster ways. There's probably slower ways. This is the way I chose. So I'm going to solve equation 1 for FAC, so I'm just rearranging it. And I get that FAC is equal to 1.673 FAD. I'm going to sub equation 4 into equation 2 here. So 4 is this equation I just, my retelling of equation 1. So I'm now going to sub that into equation 2 and solve for FAD, so into this equation right here. And I get, let's see, 1.673 FAD subs in for FAC, so that's where it's subbing in right there. So now I can put this in terms of FAD, and I solve, and that's one of the answers I need. So my first answer I've got, FAD is equal to 2.96 kips. That's interesting, right? 2.96 is almost 3. Remember that weight that's hanging is actually 3 kips. So do you think the rest of the cables are all going to just sum up to be equal to what, 0.04? No, you knew better. You knew better, right? You were like, what are you talking about? It's crazy. They won't all sum to the 3 because the 3 is the amount of forces acting that's acting downward in the negative y. But since these are all at angles and trig is really doing all kinds of, weird stuff here. And then the y components of all the cables have to be equal and opposite to that 3 kips that was acting down. That's kind of the nuts and bolts of it. But when they have y components, don't they also then have x and z components? So then all the cables start pulling against each other. So that's really kind of what's going on here. I get it. It's complicated. That's why we do Cartesian vector form and solve the system. But anyway, there was our first answer, 2.96 kips. Now we can solve equation 4 for FAC because equation 4 was pretty much just ready to go for that. So I have 2.962. I'm keeping my significant figures, answering in 3, carrying my 4 in my work. It's pretty good practice. 1.673 times 2.962 gives me 4.96 kips. That's a lot more. That's almost double, or getting there anyway, the amount of force that was hanging in the first place. When cables are acting at angles, again, strange things start to happen. Actually, not all that strange once you start believing in, science. But, just keep in mind that they're not all going to just sum to be equal to that weight that is applied. So now I can solve equation 3 for FAB because I actually have I have FAD and FAC, so this one's going to be pretty easy. And I get FAB is equal to 3.03 kips. So then my answer, putting all the values on my free body diagrams would look like that. That's them in their magnitude form. All those cables, if you had put an inline scale on them, they would each be reading that much force. The 3 kips hanging, 3.03 kips is being in FAB, 4.96 FAC, FAD 2.96 kips. We could also put them into Cartesian vector form, right? Because don't we have them from way back when on this slide? These are all of them in their Cartesian vector form. So we can just plug in these magnitudes now and get these values in their true Cartesian vector form. And here they are. That's it for this example. All of them are going to be very similar. Again, in 3D, remember the idea is just to convert all your vectors into I, J, K. Build your equations of equilibrium as scalars based on all of your i's being your x values, all of your j's being your y values, and all of your k's being your z values. And then you have a system of equations. Sometimes you'll get answers straight away. Each free body is going to be a little bit different. Sometimes you'll get answers right out of the box and you won't have to solve the system per se. This one we had to do a simultaneous solution. Each problem is going to be a little bit different, but this is how you do it. Thanks for watching.